Hi there. So, welcome back again. And we also welcome you to our free Spice Circuit Simulator software, where we have held numerous sessions and numerous models. And we want to continue with that. So, today we explore the topic of Sallen Key filter or a filter design, which is a primary component in electronic system designing. And this filter is widely used for signal processing applications in electronics. So today's topic is centered around how to use the free software, which is an open source software, particularly KiCAD, to design and analyze the performance of the filter. And specifically, we talk about the Salen Key filter, which is a special purpose and special type of filter. In our previous model, we explained what the Salen Key filters are, what its types are, and essentially it is an active higher order filter. And we also saw its comparison with the passive type of filters, which are implemented with mere RNC components or combination of op-amp and the RNC. But in this particular Sallen key type, we still use the RNC combination along with the op-amp, but the difference lies in the arrangement of these components, as you can see, and I am going to explain you in a moment, this arrangement right over here. And we will also talk about how to design this filter for a specific value of frequency of operation. And we will then perform numerous analysis and to understand its performance. Obviously, we have had numerous sessions on the KiCAD about how to sessions on using KiCAD and how to pick up the components and the devices from the library, which is right here, how to make the interconnections, how to call the sub-circuit. For example, this operational amplifier will be treated as a sub-circuit in this entire circuit. And so we have covered all these aspects. We have also covered what is this special symbol power underscore flag and why it is needed in order to have a error-free simulations, and KiCAD does that. We also explained you about how to perform and specify the analysis depends on what you want. So if you are new to this module and you are coming here for the first time, we encourage you to refer back to so many modules on KiCAD, so and also one theoretical model on Salen Key and several modules on the active and passive filters, first order and second order. So we have covered them all. So let us focus our understanding about this particular filter. So what you see here, I have used this operational amplifier from the library. I have used two resistors. I have used two capacitors, and then I have input voltage source applied to the positive pin of this amplifier. I have the negative pin of the amplifier, which to which the output is connected. And so there is this negative feedback. You can see that from the output to the negative pin, I have a negative feedback. And from the inspection, I can see that this amplifier is biased in the voltage follower mode, because to the positive pin, you have an input and the negative pin is connected to the output, or the other way around, we see that. So it's a voltage follower which can act as a buffer between input and the output of the circuit. Here is the recorded output that we will see. And is there any other observation that we would like to make? Yes, we see that there are two resistors in the series, and at the junction, we are connecting this capacitor right here, and the one end of the capacitor is at the junction of the two resistors, and the another end of this capacitor is connected to the output. So essentially, it is connected to the negative pin, and the negative pin is connected to the output. So this from output back to the junction point, which is basically coming here to the positive pin, is a sign that we see there is a positive feedback as well. So that's why the special arrangement when we do this, it's called as Sallen Key filter. And based on the specific arrangement of the impedances, now the impedances can be implemented using resistors and the capacitors. You see that at the positive pin, I have another capacitor, and other end of this capacitor is connected to the ground. So this is the specific arrangement. So based on the specific arrangement, we call it is a special type of filter, which is Sallen Key. And depending on how we place those impedances, we will configure this this filter as a low pass or high pass or a band pass filter. Obviously, you need a power supply voltage to this whole circuit, specifically to the op-amp. You have a supply pins, and that supply is being provided by this dual power supply of +5 and -5. How this arrangement is made, we have covered this in our previous session, so refer back to those modules. And in a moment, I will also explain you about this VDD and the VSS, which are the power supply pins of this op-amp, which is not specified and connected and shown here. Rather, they are separately shown on the screen. I will also show you why is that and how it is done. So finally, we'll also see how we can on the screen of the schematic itself specify the analysis. We'll do that in a moment. But before that, let us explain the basics of Salen Key filter before we do any analysis and understand the KeyCAD behavior of this circuit. So what I would like to draw here, I would like to draw for you a generic topology of the Salen Key filter. So here you can see that I have an input signal, let's say a voltage or current, and then I would say I have this impedance here, then I have another impedance. Let me call it Z1, let me call it Z2, and then I will say I have this particular combination, that is an amplifier with a very high open loop gain. The output is specified here, and the negative pin of the amplifier is tied to the output. So obviously this is my buffer, or I would say a voltage follower, non-inverting amplifier configured as a voltage follower circuit, right? What is the advantage of this? The input impedance of this Rin is ideally approximately infinity, and the output impedance of this amplifier is approximately zero, ideally. Okay, so very high input impedance, very low output impedance. So it's useful for impedance matching, and this feature adds to the performance of the filter when we do that. So coming back here, what I'm going to do, I have another impedance here. Let me call it as Z3. And right over here, this impedance is right away connected as shown in the figure. And finally, what I want to do is just a second here. I want to make sure that I'm connecting the impedance properly. Right. So what I'll do here, I will actually have the impedance here again that is connected to the ground. So I will call this impedance as Z4 actually. So you see that, or maybe let me, uh, I hope you will understand. So essentially, if you actually see that this particular circuit is right here, drawn right here. So it is just this feedback is taken like this, but in this schematic, I have drawn the feedback like this. But if you carefully observe, this circuit is equivalent to this circuit. So what I have done, I have said that, let me say my Z1 right here. I say that Z1 is actually R1. So you see here, Z1, that is the impedance, is actually R1. Okay. And then I would say my Z2 is actually R2. So you see that the Z2 actually is R2 right here. Now the Z4 is there, which is C2, and the Z3 is actually C1. Okay. So this is how I can do that in a schematic. So let me write here. I would say Z3 is actually C1, and Z4 is actually C2. So this is how, if I make such arrangement, I will have this circuit, which will be called as second order. This is like second order active filter, active filter. And in bracket, I would say this is Salen Key configuration or Salen Key topology. So this is a generic configuration, and by replacing the impedances by means of resistors and the capacitors, I can get the low pass filter. What if I want to have the high pass filter for that? So what I will do, I would like to draw your attention to draw it. What I will do is that I will have the capacitor here. I will have the capacitor here. And then at the junction, I will have the resistor here. And this is how I am making it. You can see that VO. And here, I will say this is my resistor R1. This is a C1, this is C2. And right here, I will have another resistor, not the capacitor. Rather, it will be a resistor. Let me draw here. So this is like R2. And then this configuration is same. And here is my input. So you see that I have replaced, if you compare here, the resistor has been replaced with the capacitor. Resistor here has been replaced with the capacitor. Capacitor here has been replaced with the resistor. And the feedback capacitor here has been replaced with the resistor again. So this configuration became now high pass. This is a high pass Sallen Key second order active filter. So you see now, in order to convert from low pass to high pass or vice versa, simply swap the positions of the resistors and the capacitors, and you will have this arrangement. So this is your high pass filter. Okay. Right here, so we are going forward. So I have explained you the working principle, the basic arrangement, actually the schematic of the circuit. How about the operation of the circuit? How the circuit will behave? So let me clear the drawing and let me explain you. Let's say this circuit we are talking about the low pass. So let's say at DC, at DC, at the very abstract level, we can analyze the behavior of the circuit by understanding how the components will behave. So we know that at DC, that means at frequency equal to 0, you have the transfer function, that is the ratio of output divided by input actually. So it has got, you have got this transfer function actually, TF, and it will have some value. So how we can see the magnitude of it. So we know that at DC, you have the capacitance impedance XC, which is 1 over 2 pi FC. So when the frequency is 0, this XC is infinite. So capacitors acts as an open circuit. So both of these capacitor will act as open. So in that configuration, we see that you have got input signal. You have these two resistors, R1 and R2, but what you see here, you got this amplifier. This capacitor got open. This capacitor got open, that is C2. And you have this capacitor also, that is also open. And right here, the rest of the arrangement is same. So what you see here, I have open circuit, no signal path, and there is a amplifier. So essentially, I see that this circuit, you have an input signal that is coming to the positive pin, and this amplifier, since it has a very high open loop gain and it is configured as a buffer or a voltage follower, the output voltage will be equal to input voltage. So it is the output voltage divided by input voltage. The gain is 1, or in dB it will be 0 dB. Okay, so the transfer function, the Bode plot will look like this: VO divided by V in. You see that you start right here. So here you say that your gain is 1 right over, and this is your frequency, that is frequency. This is your plot frequency. Okay, F, or let's say omega, that is 2 pi F. Okay, so this is here. Now, let's say how the circuit will behave when you have, let's say, at f equal to infinity. So obviously, when f tends to infinity here, Xc is 0. So capacitor acts as a short circuit. So can we draw this configuration? You have these two resistor, you have a signal, R1 and R2. This capacitor got short, and this capacitor also got short. You have this signal, that is C2. Here is your C1, here is your C1, and here you see that you have an amplifier, positive and the negative pin, and this is your V output. And what you see now here, well, at this voltage, you have got 0 volt because capacitor got C2 got shorted. So here is 0. Amplifier gain is actually very high. Therefore, both the voltage at both the positive pin and the negative pin should be at the same potential. So this, due to virtual short, this 0 volt comes here. The 0 volt is nothing but the output. So output is actually 0, and therefore output divided by input is 0. So we'll see that at a very high frequency, right here, the output is 0, the gain is 0. But there is like at a frequency, let's say at f equal to 1, f equal to fc, where fc is the cutoff frequency of this filter. So cutoff frequency is a frequency where the filter response is divided between the pass band and the stop band. So here is the pass band of the filter, and this is the stop band of the filter. So you can say that the response will look like this. Okay, the response will look that, and somewhere here that frequency fc will be there. So this is called as -3 dB point, where the cutoff frequency is. And this, you can see that this is a low pass filter. So at the low frequency, you have a gain. At a very high frequency, you have 0 gain. So that is how the behavior of this circuit can be explained. Okay. So I have cleared all the drawing. Now coming back to our KiCAD. So what I have done is that from the library, I have actually chosen this amplifier TLV9062. But before that, I want to explain to you how I chose these values of the resistors, which are 10K, how I chose the values of the capacitors, which is like 1.1 nano each. So let me calculate, keep it the same, 1.1 nano, or you can change there whatever you want. So obviously you need to know the transfer function of this filter. So second order transfer function for higher order, which is the second order, Sallen Key active filter, we are going to write the transfer function for the second order active Sallen Key filter. So here is your transfer function. So before that, let me write to you the generic model that we have drawn earlier. The generic model, what was the generic model? The generic model was here. This was your Z1, this was your Z2, this was your Z4, and this was your Z3. You remember before some time we have drawn this. So for that, actually, you actually can say that, let me just write here. For that, you can say that VO over V in can be written as, which is like a transfer function, Z3, Z4 divided by Z1, Z2 plus Z3 in bracket Z1 plus Z2 in bracket close plus Z3 into Z4. So this is the transfer function or the voltage gain expression of the generic filter topology. But since now we have replaced these values of resistors, you can simply plug the values of Z3, Z4, Z1, Z2. So obviously Z1 is R1, Z2 is R2, Z3 is in Laplace 1 over SC, that is your C1 of S, and Z4 is 1 over C2 of S. In the Laplace domain, you can write that, and just plugging those values to get the final expressions. Okay. For the second order filter in the Laplace domain, for the second order active filter, low pass, the transfer function is expressed as h of s is equal to omega naught square divided by s square plus twice alpha s plus omega naught square, where omega is the undamped natural frequency, which is derived as 1 over square root of R1, R2, C1, and C2. So we are talking about this filter now. So you see now, with the values of R1, R2, C2, and C1, I can get the value of omega naught. So for example, if omega naught is equal to 15 kilohertz, this is the given frequency for which I am asked to design a frequency, design a filter for this frequency. So I know the value of frequency, and with that, I have to choose the value of R1, R2, C1, C2. But there are now 4 unknowns. So how we do that? That is the question. Okay. So what I can do to this expression, I can write this expression again. So I know that value of omega is given right here. So this expression will be written as h of s is equal to 1 over R1, R2, C1, C2, obviously taking the square of both the sides divided by this s square remains there plus s will be there. The 2 alpha, alpha is the attenuation factor. So I will say 1 over R1, C1 plus 1 over R2, C1 bracket close plus 1 over R1, R2, which is omega naught square, C1, C2. So that's my transfer function actually. So you basically must be thinking how I am arriving at this expression. So we have covered these expressions and we have got the expressions for omega naught. We have got the expression for alpha. We have got the expression of quality factor Q. And we have got the expression for the H of S in our previous theoretical module on the Salen Key filter. So if you are coming here for the first time, we encourage you to refer back to that model, which is given here in the playlist also, and you can search it. Okay, so in another word, let me write here the H of S for this low pass filter actually can also be written as, because we know the formulas for all these parameters. For all these parameters, we now know the formulas which is expressed here. So H of S this then can be written as 1 over, let me write here, 1 plus C2 R1 plus R2 into S plus C1 C2 R1 R2 S square. So if you see that I want to express that this term is basically 1 over omega naught square, and this term is actually twice zeta by omega naught, which is equal to 1 over omega naught into Q. So that's how I actually can get to this expression. But how I got to this expression, because I assume some design formula I used, R1 is equal to M times R, R2 is equal to R over M, C1 is equal to N times C. These are my design formula. C2 is equal to C over N. So in the previous expression. So if I use these formulas where M and N are some factors, okay, so I can reduce my expression of the frequency of omega, which is right now this one, to the value of 1 over RC. So what I'll do, I will choose R1 equal to R2 and then R1 equal to. So with this formulas, I got the reduced expression for the omega naught, which is 1 over RC. Earlier it was this expression. And then I can say that R1 is equal to R2, as you can see right here, and C1 is also equal to C2. So as you can see, therefore I can have this kind of expression. Okay. In fact, yeah. So because R1 is equal to R2 and C1 is equal to C2, if I put these values in this formula, I get this value, omega equal to 1 over RC. Okay. So I think so. With that, I got these R and C value here, very simplified. I know omega naught is equal to 15 kilohertz. So I selected R equal to, let's say, 10K ohm. And then I got the value of C from this formula, omega equal to 1 over RC. So C comes out to be 1.1 nano. And that's it. So I have got, let me clear all the drawing. And now we are very well set to explain our KiCAD and how we are actually doing the real world design of active second order active Salen Key low pass filter. So in a moment, I'm going to demonstrate you that. Oh, very good. So we have done the understanding about how we got the values for R and C. We are having the frequency omega naught is equal to, let's say, 15 kilohertz. And accordingly, from the transfer function, we understood how we did that. So what I'm going to tell you now, from the library, I picked up these components. Like I clicked here and look at this, it is loading the symbol library. And once those symbol library has been loaded, which is now loading the footprint library right over here. So step by step, we are actually doing good. And it is taking a while, but it is worth waiting. And loading the footprint libraries, it takes a little bit of time and it is done. So I will type R, simply R, and there is a register right here. So this is how I chose register. And then I place that, I clicked OK, and I place that on the schematic. So I have explained this in the previous session. Similarly, I chose the capacitor. Once I chose the capacitor, I can just simply double click on the component. And then here I can write the value. Okay. And you see that if you click the simulation model, basically I'm using the built-in SPICE model for resistor and the capacitor. So here is the device capacitor, device type is ideal. I have an option here also. Okay, similarly for the resistor, I have ideal, whatever I want to choose. So cancel, let me show you for the resistor. Here, double clicking, I can choose the value here. Click simulation model. There is a ideal built-in SPICE model, which is ideal, 10K value. I have done that. So cancel. Now, power supply, I just click the symbol library again, and it is opening again. Then I said VDC. So you see that already placed. I got the symbol for the VDC. Okay. Then I have to, this is in fact DC voltage source. Actually, I want DC voltage source. So here is the symbol for the voltage source. But how about these flags, VDD and the VSS? So I have to type that. So let me type VDD. It will have this VDD symbol. If I type VSS, it will be VSS. And here it is VSS. So this is how actually I done that. Okay. So cancel. Similarly, I got the symbol for the power flag. So we have explained this so many times in our previous session. Now, look at this guy, TLV9602. Why only this part from the manufacturer? This is not a generic model. This is a SPICE model for a specific IC, integrated circuit dedicated for op-amp. So why I have chosen that? Because I want to do the real world design. I can use the generic model of the op-amp also. So I need a SPICE model of this. So for example, I just click the component library here first. And then I typed, just a second here. Yeah. So here I searched for this part number, that is TLV909062. So here it is. So I have got this amplifier, dual amplifier. This is dual op-amp. So in one IC, you have two pieces of op-amp. This is available in these packages. So if I click this arrow right here, so it has got 3 units. This is unit 1, which has pin 3 to 1. 1 is the output, 3 is the input, and 2 is the input. So this is exactly what I have done here. So it is called as UA1, U1A actually. Then if I say unit 1, which is right over here, If I click unit B, so you see it's the same one, but pins are now 5, 6 for the input and 7 is the output. And the third, unit C, is this power input pins. So this is pin number 4 and pin number 8 are used for uh, negative and the positive power pins of the op-amp respectively. So again, I see that it is a dual operation amplifier IC. It has got total 8 pins. So first 3 pins, 1, 2, 3 for the unit A. Next 3 pins, 5, 6, 7 are for the unit B. And this is pin 4 and 8, which is what I have done here. You see that? Because so I chose only one single unit because I need only one piece of that IC. It has got 2 pieces in the single IC. So what I done, in fact, if I want second op-amp also, so what I'll do is I will just click OK. Is there any other information for that? It is given the manufacturer information. Then there is like data sheet available from the manufacturer. You can click here if you want to see what is the gain, bandwidth, offset voltage, and so many other parameters such as slew rate, etc., common mode rejection. So you can just click here when you use this one. Okay, otherwise just say okay. And so if I want this, if I place this component right here, then press escape because this part reflected now. Okay, because this has to be placed here. So I have used all UA1, U1, U1A I have used, U1B I have used, and U1C I have used. Okay, so full IC I have used. But since for this specific explanation, I don't need this part, I will just delete. I will keep these 2 parts, U1A and U1C. This is out. So, and after that, I have done these connections. And then if I click here, I will show you how to add text. So there is an option here, add labels, which I have done here. Like just double click here and it helps me to add the label. I can just write V output. For example, I'll say V output. Okay. And this is my V4. That is the voltage source which has got DC voltage of 0. It has got amplitude of 1 volt, frequency of 1 kilohertz, and the AC's magnitude of the signal source is also 1. So all kind of analysis depends on which analysis I do at a time. Accordingly, the specific category will be selected. Okay, for the DC analysis, DC voltage will be done. For the transient, I can have a peak value of the signal. For the AC Bode plot, I can have this value of the signal. For the transient and the AC analysis, I can specify the frequency. So done that, let me show you what else I can do. This is at global level and add sheet here. Here add text. So if I click here, I have got this box. So I can type anything here and just say I place it here. This is what I have done. So let me undo it. So if I double click here, so what I done, I have specified I want to run the AC analysis for my circuit. So I said that, okay, .AC, DEC decades, run it from frequency of, decades means 10. Then one start with the DC frequency or 1 hertz and stop at 1 mega. So this is the SPICE syntax. So other way around, what I can do is first, let me check the ERC. Similarly, you can see that this is extra syntax. Double click here and you see that the dot control version dot NC. That's about your sub circuit. So op-amp is sub circuit here. So what you can do instead of specifying here as a text, this command, you can open the simulator. But before that, let me show you here, ERC. We'll perform ERC, errors and warnings will check for run ERC. We have got 0 errors. There are some warnings although. So there are warnings here, but for now we can ignore that. We are concerned about errors. That's it. Click OK. Okay, so I have trouble here in getting the time domain simulation for this circuit. I have to maybe troubleshoot it properly because in the output, you see that this is my output and here is an input. But for applied 1 kilohertz, 1 volt peak signal, I'm not drawing any output here for the time domain case. So I need to check that, okay? For the AC analysis, it looks perfect as we saw initially. So we'll cover that in a subsequent section. And also in case if you find out the answer, how to, you have a KeyCAD, I guess now. I just try to implement this circuit as an exercise and show your results in a time domain and put your answers in the comment section. So we'll stay tuned. We'll explore more on this circuit in the next part. Okay, see you then.